Hey everybody, welcome back to this afternoon's session. My name's Steve Reding. It's tremendous to be here and be part of this amazing initiative that Matteo and GCAP have put together, and it's great to meet you all today. Looking forward to talking more this evening over dinner and drinks after today's session. So what I'm going to try to do in my session is talk now a little bit about global trade. Building on from Matteo's comments this morning, I'm sort of incredibly optimistic and enthusiastic about the field of international, including both macro and trade. And as I'm sure you're all aware, with rapid changes in trade policy here in the United States and other countries around the world, international trade and trade policy is a very exciting part of the field of international economics. So what I'm going to try to do today is roughly try to do three things in the lecture. The first is just to sort of introduce some of the sort of classic sources of international trade data. And so in trade, we're sort of rather fortunate in the sense that the historical infrastructure of microdata has been much more widely developed than it has in international macroeconomics and international finance. And so Matteo and the research team here at GCAP have been amazing in kind of putting this new microdata together, whereas in trade, we've kind of already had that. So I had that for a much longer period of time. But I'm just trying to kind of lay out to you what are the main sources of data that are easily available, what are the advantages and the disadvantages of each of them. And then I'm going to kind of connect with some sort of classic models from international trade that many of you will have taken trade courses, and so you're going to be very kind of familiar with those models, the sort of class of constant elasticity trade models. So I'll be playing with some of the properties of those models, showing how you can linearize them and get a very nice way of computing the exposure of each country to shocks in any other country in the world. And so the sort of linear algebra representation of those models is sort of very powerful and very useful for a number of reasons. And then towards the end of the lecture, I'm going to try to connect the material I've talked about, namely on sort of classic models of international trade, with models of international macroeconomics and international finance. So as Matteo mentioned this morning, over time there's kind of a convergence where parts of the international trade field now are becoming increasingly close to macro and international macro. And so there's kind of a very kind of creative area of research at the intersection of those two fields where I think there's still a lot of exciting work to be done. And so I'll sort of talk about some of our work where we're sort of trying to combine some of the sort of classic mechanisms in trade models together with mechanisms from international macroeconomics. Cool. So let's sort of dive in and talk about sort of data sources. Some of you may be kind of aware of all of these, but I just want to kind of lay it out for those of you who are less familiar with the trade data, maybe point to a sort of few alternative sources that you may not have heard of. So modern world trade data are pretty easily available, very, very widely available. So as I'm sure many of you know, the United Nations Comtrade database covers the entire world trade. It's compiled by the United Nations, available since 1960. It reports trade data by harmonized system 6-digit product. There's around just under 10,000 of those 6-digit products. Individual countries often report data at a more disaggregated level. So for example, the United States goes all the way down to the 10-digit code, and there are around 19,000 of those. So pretty disaggregated. An example of one of those 10-digit products might be leather, baseball, gloves, and mitts. Pretty finely detailed categories of products. Other countries report at a slightly higher level. European Union, I think, goes down to the 8-digit level. And so all digits after the 6th one are specific to a country or to a group of countries such as the European Union. Whereas the HS 6-digit products are common worldwide, and so the United Nations Comtrade database reports data at that level of disaggregation for the whole world from at least the 1960s onwards. And so many of you will be able to access those data directly from United Nations Comtrade through your university libraries. For example, when I was at Princeton University Library had a subscription to those data. There is a kind of shortcut, though, to kind of make the data even more easily accessible for those of you who want to work with these types of data. CEPI in Paris have put together the BACI trade database, where they've essentially cleaned up the United Nations Comtrade data for you. And so at least for recent years, the most easily usable data is from 1995 through to 2023. They've actually taken all the years of United Nations data, and importantly, because year to year or occasionally every certain number of years, the harmonized system changes. The exact definition of products can change as new goods get created, like the iPhone and so on, or the revisions to the existing set of goods as some goods are no longer relevant. The exact classification changes over time. And so CEPI has kind of made things easy for you by mapping goods between those classifications. And so the data are available according to the Harmonized System 92 classification on a consistent basis all the way from 1995 to 2023. And then if you're only interested in shorter time frames, they also report data using later years of classification. So for example, 96, 2002, 2007, and so on. So that's a really great resource if you really want to be able to have data on trade between many countries at a finely detailed product level. One limitation of those data sets, though, of course, and I want to emphasize that now because this has been important in trade in recent years, is there's not much information at the firm level about individual firms importing and exporting. So if you're interested in sort of matching and searching, matching between buyers and sellers, these data are not going to be as suitable, and I'll say more about sort of alternatives if you really want the firm level information. But nonetheless, really great source of data for studying changes in comparative advantage over time. If you want to go the kind of much longer historical time periods, there are some other data sets that you may want to consider. So CEPI, again in Paris, has what they call the gravity trade database, where if you're only interested in aggregate country-level trade, you can get the data all the way back to 1948. So you can do really long-term analysis of trade policy, how it affects patterns of trade. So for example, Keith Head and Thierry Meyer have a paper on colonial linkages and how those linkages abate over time as countries become independent. So again, but there, the limitation is it's only aggregate trade between a pair of countries, US, Mexico, in a particular year, the aggregate value of that bilateral trade, and then those data are reported for all other bilateral pairs. That source, though, is also convenient because they've done the work of combining those trade data with a lot of the standard variables you might want to include in a gravity equation. So as I'm sure you're all familiar, a whole class of trade models predicts a gravity equation for bilateral trade flows. I'll be saying more about that later. Often when we model trade, we're going to kind of regress bilateral trade on importer fixed effects, exporter fixed effects, and then some measure of bilateral frictions, such as bilateral distance, common border, and so on. And so the CEPI gravity database has all of those characteristics, various different measures of distance, proximity, colonial relationships, political relationships, language relationships between countries. If you want to do history and disaggregated products, there's kind of a third source to think about, which is the NBER World Trade Database that was put together by Rob Feenstra, released an NBER working paper in 2005. And so the caveat with this data set, it's got a big advantage. Big advantage is it goes all the way back to 1962. The big caveat or disadvantage is it stops in 2000, although Feenstra has maintained some later versions of the paper and of the data, and if you reach out to him, he'll often give it to you. But the sort of official data from the NBER finish in the year 2000. Okay, so if you're interested in any of those databases, these slides have active links, so just click on the brown link. It's going to take you straight to the data source. Final sort of pointer, again, for kind of long-term data on bilateral trade between countries. The IMF Direction of Trade Statistics, DOTS database, also goes back to 48. It's one of the official databases that the CEPI gravity database I mentioned earlier draws on. They include the DOTS data and then also some other sources of long-term trade data. Okay, so those are kind of some of the leading sources of modern trade data for those of you who want to get detailed information on bilateral trade between countries, potentially down to the product level, to think about sort of patterns of comparative advantage. Often when we kind of write down trade models, we want to go a little bit beyond that, though. We want to sort of think about input-output linkages within the economy, because one of the big limitations of trade data is that they're reported on a gross basis. So when the iPhone is imported from China, historically into the United States, the good valued at the border is the value of that iPhone as it crosses the border. Obviously, not all of the value added in that iPhone was created in China, the point of final assembly. Some of the chips may have been made in Japan or elsewhere in factory Asia. And so, a big limitation of the observed trade data is their gross flows. They don't break out the whole value added chain. And often when we write down models, we're kind of interested in global value chains, input-output linkages, and so on. So for those of you interested in kind of bringing that information in, there are sort of two main ways in which to go. One way in which to go is to sort of take the gross flows data that you see reported and then feed it into a model that explicitly models those input-output linkages. And so a classic example is sort of Caliendo and Paro in the Review of Economic Studies, studying the welfare effects of the North American Free Trade Agreement. And so now people in trade have done a pretty good job in putting together comprehensive input-output databases for many countries around the world. So probably the most commonly used database is the WIOD, the World Input-Output Database. That's, for example, used by Arno Costano and Andres Rodriguez-Clare in their handbook chapter on quantifying trade policy. So that's going to give you input-output matrices for 43 countries in the rest of the world. Data reported for 56 countries using the International Standard Industrial Classification. So sort of standard classification of production industries maintained by the OECD. It's going to be more aggregated, substantially more aggregated than the trade data I talked about. So here we've only got 56 sectors, but it's going to enable us to model those input-output linkages. There's also another source of input-output linkages, the AORA Global Supply Chain Database, which when you first hear about it, it sounds amazing. It sounds really exciting. So, intersectoral flows around 15,901 sectors across 190 countries from 1990 to 2022. Sounds amazing until you realize that most of the data are actually imputed. So, there's a big kind of health warning with this database. But nonetheless, that's a sort of another source where people have tried to put together the data on input-output matrices, but it's really worth reading the fine print and the footnotes as to what's actually data and what's been imputed and how the imputation's been done. So that's one way you can go to try to build in global value chains, is actually use the model to model the input-output linkages and feed in the input-output matrix. The other way you can go is, of course, to try to sort of transform the data and construct trade and value added. And so Robert Johnson at Notre Dame is perhaps one of the sort of leading people who sort of pioneered that approach. And the OECD maintains a database on trade and value added, the TIVA database, which again you can download from the brown link here. There's sort of, again, there are some sort of caveats. And what is the caveat? Well, how do we go from gross trade flows to trade and value added when we don't see separate input-output tables for each importer with each of its exporters? Typically, each importer just has a single input-output matrix, like we see in the World Input-Output Database. Well, the only way we can do that is by making a kind of proportionality assumption. And the sort of typical assumption is that when a country exports, it's using the same input-output structure with all of the partners that it exports to. And so again, there's kind of a big caveat there. And in some sense, that should be closely related to just modeling the input-output structure in your model, rather than just using the trade and value-added data. But those of you who are kind of interested in directly measuring trade and value added, that's one of the sort of most kind of comprehensive attempts to correct the gross flows, trade data, to deal with global value chains. Okay, so that's one side of international trade, is the kind of the actual flows between countries. But obviously one of the things trade economists are interested in, and it's particularly policy relevant these days here in the United States, is thinking about trade policy. And obviously by far the most prevalent trade policy is input taxes or tariffs. There are several different sources of those data for research. The original kind of meta source for all of them is the United Nations Trains database. Trade Analysis Information Systems database, which reports tariff data by country, partner, and product according to the harmonized system 6-digit level. Okay, so again, same level of classification as the United Nations Comtrade data. Strength of the Trains database is it actually reports both the most favored nation tariff for a country. Well, I'm not going to pick the United States, maybe a bad example here, given recent changes in trade policy. But say for Canada, it reports Canada's most favored nation tariff. So that's the tariff that's agreed to under the terms of the World Trade Organization, and that it offers to all of its trade partners. But then often countries, and Canada is a good example historically, often may sign free trade agreements with specific partners. And so there will also be some preferential rates. And so free trade agreements allowed as an exception under the World Trade Organization. And so until recently, there were no tariffs on US-Canada trade. And so the preferential tariff would be 0 on US-Canada trade historically. And so the Trains database reports both the most favored nation and the preferential tariffs. So good example here of why you should always look at data when you use it. These big databases are very sort of intimidating just because of the number of observations. But Fyodora Tetti, who was a postdoc at the University of Munich, she just recently spent a year at Princeton. She kind of pointed out this sort of major flaw with a lot of people who'd been using the United Nations Trains database. So what's that major flaw? Well, the most common window through which people access the Trains data is this World Integrated Trade Solutions database, the WITS database maintained by the World Bank. And as I mentioned, trains has both the most favored nation tariffs and the preferential tariffs. But the sort of footnotes, or the sort of thing some people hadn't noticed, is that countries don't always report the preferential rate every year. And so if you were to look at the data reported, say, for Canada and the US, in some years when the preferential rate is reported, the tariff would be zero because it's a free trade agreement historically until recent times. And then in the years when the preferential rate wasn't reported, nothing was reported. And so people were just sort of imputing the most favored nation rate. And so unless you sort of take account of the fact the preferential data are only reported in some years, if you don't realize that, you can end up with these sort of sharp tooth-shaped measures of tariffs over time. And it's a fun example. Those of you who want to look at Feodora's paper, she mentions some really influential papers in the trade literature where the tariff data was just one input. It wasn't the focus of the paper, but where it was subject to this sort of missing data problem and false imputation. And so Feodora actually has sort of taken the United Nations Trains database, and she's dealt with that issue, sort of recognizing that the preferential rates are not reported in every year, and she's made available the database to you. So for those of you who want to use tariffs around the world, it's kind of really important to use Feodora's database, or to clean up the WITS data by yourself, at least be aware of this issue with the trade policy data. This is not trivial. So Feodora finds when you sort of re-estimate the specifications in some published papers, you find that the trade elasticity changes quite noticeably when you use the correct tariff data rather than the falsely interpolated tariff data. So, good example in science, always useful to look at the data. It's easy to say that, difficult to do when you have vast databases, but, it's a great example of where just looking at the properties of the data can be super informative. Okay, so one of the features about trade and production is, sometimes you have production data reported according to one classification. So in North America, that will be the NAICS classification, the North American Industry Classification. But then your trade data may be reported at a different classification. As I mentioned, they're typically reported according to the Harmonized System classification. So there are some great public goods out there in international trade, which I just wanted to kind of make everybody aware of if you didn't already know about them. Peter Schott's website at Yale, he has a number of very useful concordances, both for different versions of the harmonized system classification over time. As I mentioned, it changes over time. And then also between things like the NAICS classification and the harmonized system classification. And obviously, if the mapping is one-to-many, it's often very easy to put those concordances together. But sometimes there can be many-to-many mappings, which are kind of very complicated to deal with, and you have to make various alternative assumptions. And so actually being aware that there actually are these standard resources out there that can at least provide a starting point and help you save a lot of time can be quite useful. As well as Peter's website, there's another website maintained by the Forum for Research in Empirical International Trade. They organize several empirical trade conferences each year. So those of you who are working more on the trade side of international, I definitely recommend those empirical trade conferences. I've attended them many times myself and learned a lot, benefited greatly from attending them. So that's sort of one call out for them. And in addition, their website also has a number of other useful concordances and other links to data. Okay, so just to sort of flag that as trade researchers, as one of the issues we have to deal with is potential different classifications in trade and production data. And then finally, because in some of my work, I've tried to use historical variation. Why? Because often when you look back in history, there may be a natural experiment, there may be an exogenous shock, which actually helps shine light on a particular economic mechanism you're interested in. And so actually using that historical time period gives you the exogenous variation you're looking for to try to pin down the things you're interested in. And so I just wanted to mention that with digitization, the fall in the cost of computing power, it's now increasingly available to be able to get hold of data on historical trade flows a long way back in time. So these are the sort of three most widely accessible historical trade databases. There's a Federico Tena World Trade Historical Database. So focuses on the period 1800 to 1938. So obviously the main limitation there is it sort of stops before the Second World War. But it gives you, historical coverage, and the data are reported by the sort of polities at that point in time, the country boundaries at that point in time, which are obviously in some cases quite different from modern country boundaries. Perhaps the best source of historical trade data is again from CEPI in Paris, the TradHist database. So that reports data on a sort of consistent basis for 188 years, from 1827 all the way through to 2014. So that gives you really, really long horizon trade data. Some great examples of papers that have used that in creative ways. Jim Fira has a really nice paper on the Suez Canal, looking at the closure of the Suez Canal during the Arab-Israel War in the Middle East. And then there's some other work on the Panama Canal and so on. So with that historical time frame, you get these sort of dramatic changes in the structure of trade that you can potentially use to estimate the effect of trade costs on trade flows and so on, and look at the speed with which adjustment occurs. So the Seppi Tradis is probably your best bet if you want to go really back in time. There's also a competitor to Federico Tena, the so-called Ricardo trade database, which again has data, but just for a historical period. So just some sort of shout-outs there about various possible sources of trade data for those of you who want to do empirical research connecting with trade data. Has anyone got any questions there about the data, just before I sort of get a little bit into the main meat of the model? I just want to spend a little bit of time outlining those sources for anybody. Happy to take any questions. Let's talk more later. Yes?
So if I'm interested in non-tariff trade barriers, there is no data at all.
Great question. So yeah, measuring non-tariff barriers, for obvious reasons, is extremely hard to do. The data are limited. The trains database does actually have some information. Sometimes it has data on, for each product, what are the number of non-tariff barriers, or like an indicator variable for whether there is a non-tariff barrier. And so people sometimes calculate things called coverage ratios, which are things like within this two-digit sector, what fraction of products have some form of non-tariff barrier, or what fraction of trade values have some form of tariff barrier. And obviously the issue with trade values is they're affected by the barriers and so on. But yeah, it's hard to do, but Trains has some information on that. For individual countries, people sometimes try to estimate the ad valorem equivalent of the non-tariff barrier. That's obviously what conceptually you want to do in terms of a trade model, but that sort of typically requires more information to do that. If you want to get information on many countries on non-tariff barriers, the Trains database is one of the best places to go, or to sort of drill down to things like the multi-fiber agreement, where if you're just interested in textiles, you might be able to get more data on the details of quotas and so on. Cool. Awesome. So that's pretty much what I wanted to say, almost what I wanted to say about trade data. Final thing I just wanted to mention is for those of you who are interested in the United States, as I said at the beginning, there have obviously been large changes in recent trade policy. It's quite sort of exceptional to have such large changes in tariffs from a relatively low level in such a developed country. And so with the tariffs introduced by the first Trump administration, there have been a whole bunch of papers that have used the impact of those on various outcomes of interest. So Pablo Fagelbaum, Penny Goldberg, Patrick Kennedy, and Amit Khandelwal have a really nice paper in the QJE on the return to protection, looking at the sort of welfare impact of those tariffs in a general equilibrium trade model related to the model I'm going to develop in the lecture later today. I've done some work looking at the price effects of those tariffs. And then a whole bunch of people have looked at input-output linkages, global value chains, and so on. Often those papers have replication data sets available. So for example, my papers, you can download the replication data sets, and then you've got the combined trade and tariff data for the US. And I think in our paper in the AEA Papers and Proceedings, we go from sort of 2016 all the way through to October 2019, shortly before the COVID pandemic. So, and I'm sure there's much more work still to be done on trying to understand features of those introduction of tariffs. I'll say a little bit more about that later in the lecture. And then obviously in the second Trump administration, we've seen a further change in trade policy. There are several papers out there, some of you may be aware, of people starting to analyze those data. The trade data are reported with a lag, so often the data don't arrive for a few months, and so we're sort of still waiting for the data to come in. And one of the challenges with these recent rounds of tariffs is that even when announcements have been made, there's obviously a lot of uncertainty as to how long those tariffs are going to remain in place for. There's often been a 90-day pause, and there's negotiations between countries. And so it's not just the level of protection changing, but also a change in uncertainty. And so just to flag that. Again, continuing to think about the US, as I mentioned earlier, a limitation of the United Nations Comtrade databases and the other ones I mentioned is they don't have firm level identifiers. They don't tell you anything about the firm. So you can look in a rich detail at country comparative advantage across products, but it's hard to do anything on firm heterogeneity, think about models of heterogeneous firms and trade and so on. Those of you interested in working with the type of data which gives you firm level trade information, In the United States, the gold standard is the linked firm trade transactions database, which is available from the Census Bureau. It requires you to have access through a census research data center. And so those of you who are interested in working on the United States, having the firm information, that's the way to go, is to put in a proposal. Anyone can submit a proposal. It can take up to 6 months to get approved, so it's good to do it earlier rather than later. The way that proposals are judged is in terms of enhancing census's ability to fulfill its mission, to monitor the American economy. So when you write your proposal to access the data, it's not enough just to talk about why your paper is economically important because you're testing a model or testing a key hypothesis in trade, but it's also worth making clear how your research project is going to help the census learn more about the American economy because that's ultimately the Census Bureau's mission. So just to kind of flag that for those of you who are interested. And then if you don't want to go the linked firm trade transactions database, you don't want to go that route because of the sort of delays and so on, there are a couple of other options out there, and I just want to mention them. And again, their limitations, not everyone's aware of them. There is a whole bunch of alternative sources for what's known as bills of lading data. So when goods are loaded on a ship, a bill of lading is completed that tells you who's the shipper, who's it being shipped to, what the product is, what port does it go through, what the mode of transport is, and so on. Those data are pretty easily available from private companies. So DataMine is one of the leading companies. Panjiva is one of the other leading companies. The big caveat, not everyone's aware of this, is that those data do contain trade values, but they're imputed, right? And so it's at least in the United States. In the United States, the values of the transactions is confidential information. If you want the true values, you have to apply through the Census Research Data Center, as I mentioned. So how does Panjiva come up, or DataMine come up with values? Well, they essentially impute them based on the public data. So they know that the Census Bureau reports the total value of trade for each product. It reports the total value of trade for each country and so on. So you have various sort of aggregations of the microdata, and you can use those aggregations, feed them into an algorithm, and try to predict what the unobserved trade value is. And so just to kind of, again, you should kind of know that and be aware of that if you want to use those data. For some countries, Panjiva actually does have the reported values. So I believe in Mexico, the bills of lading actually do contain the true values that are the same as the official customs values. But for most countries, they're imputed. So again, just to flag that. Okay, cool. So now I'm going to start transitioning to the, yep.
On that point, historical bills of lading data?
Great question. So I guess in principle, there are things like that. So Britain is the country I know best. So there are customs ledgers that record imports by product, by country, that are all like handwritten for Britain. There are also port books for individual ports in Britain that tell you which ship came in, what it contained, typically lists for each ship all the main items included in the shipment. It's not going to be as rich as the modern bills of lading data, but it's something like that. And most countries have some form of historical ledger like that. And it varies by country what exactly is recorded. It's typically recorded in handwritten once you get back to the sort of 1800s and so on. But related to Melissa Dell's talk tomorrow, there are now increasing algorithms enabling you to kind of digitize handwritten records. And if we go closer to the modern day, there probably at some point were also printed bills of lading, but it's just a question of how many of them have survived. Digitally for the United States, I'm not aware of anything before I think like the late 1980s, early 1990s is the longest you can go back in the digital data, and I'm not aware of any sort of printed forms before that. It could be there lying around in a warehouse somewhere, but I've not heard about them. But yeah, it's a great question. So now I'm going to transition a little bit to the sort of main meat of what I wanted to talk about today, which is to kind of connect with a classic set of models of international trade that many of you will be familiar with, so-called constant elasticity trade models, and then showing them how you can use them to construct these sort of rich measures of the network of trade and countries' networks of exposure to shocks in other nations. So all the code and other resources for everything I talk about today is going to be available online. So the main code is on this website here, internationalfriendsandenemies.com. You can also get it from my webpage. It has the replication data and code. It also has a whole bunch of interactive maps and network graphs. So you can actually graph the network of world trade, how it evolves over time, pick your country of interest, your year of interest, and so on in an interactive way. And then I'll also connect a little bit later to a subsequent paper where we kind of combine the trade model that I start with some dynamics, and I'm going to be talking about some dynamics later in the lecture today. So again, on my website, I have a replication archive for that paper as well with all the code. And because the dynamic model is a little bit involved, to make it particularly easy to use these techniques, we also kind of created a model toolkit, which is essentially creating like a Monte Carlo of a little simulated model economy, and then showing you how to implement our code for that model economy in a way that's sort of as transparent as possible to kind of make it as easy as possible to use these techniques for characterizing the transition path in dynamic models. Okay, cool. Cool, so let's get into the main meat of the lecture. So I'm going to begin by talking for about half of the remaining time about this paper, International Friends and Enemies, which is going to connect with the sort of standard class of trade models you're all familiar with. I'll show you how we can construct these measures of the network of trade. And then in the second half of the remaining part of the lecture, I'm then going to show you how we can take one of those models and combine it with an international macro model and try to connect the trade flows, the mechanisms we think about in trade with some of the classic mechanisms people in international macro are interested in, try to kind of connect these two fields together with one another. And in that second part of the lecture, I'm going to be using some of the CPIS data that Antonio mentioned earlier, and I'm going to be building on the GCAP's restatement of the data from residency to nationality. All of that's going to be kind of feeding into the model. And the paper I'm going to talk about first is joint with Ernest Liu and Benny Kleinman, and the paper I talk about later will be joint with them and then also Moto Yogo. Cool. So what was the motivation for this paper? Well, we were sort of really interested in this debate about geopolitics, which is part of this year's session and GCAP. So thinking about the idea that when you look around the world and you see major changes in the relative economic size of countries, they're often accompanied by major shifts in the balance of political power. So obviously thinking today with the rise of China, there's a lot of informal discussion of China gaining increased political influence over countries through the Belt and Road Initiative, through its trade linkages with countries, particularly in sub-Saharan Africa and in other emerging economies. If you look back in time historically, people also talk about the conflict between Britain and Germany towards the end of the 19th century, beginning of the 20th century, as another example of where an initially large country, Britain, was faced by an emerging challenger, Germany, rapidly becoming of similar size or even bigger size over time. And so I want to kind of think about that idea that changes in the economic size of countries might be accompanied by shifts in the balance of power. And so in order to think about that question, I'm going to need an economic measure of how dependent is my country on another country. And so that's where we're going to use this class of constant elasticity trade models to try to provide exactly a micro-founded, rigorous measure of the extent to which I'm economically dependent on another trade partner. Okay, and so we're kind of interested in a hypothesis that as countries become more economically dependent on a trade partner, do they realign politically towards that trade partner? The sub-Saharan African countries have become more dependent on China for trade and their growth. Have they started to vote in similar ways as China, to support, to form political treaties with China, to become more closely aligned politically with China? And obviously that's a challenging question to answer for a couple of reasons. Well, one is, well, how do you measure how economically dependent one nation is on another? I can't just look at the bilateral trade flow because that's a sort of partial equilibrium measure. How dependent I'm on one country depends upon what my outside options are, what the choice set is, and how much I trade with other countries in that choice set. And so I need to think about in general equilibrium. I need to have a measure of dependence that's consistent with general equilibrium in a class of trade models. And so that's one of the things we're going to try to do. So we're going to say that a country is an economic friend of its trade partner if growth in that trade partner raises the country's income. And a country is going to be an economic enemy if growth reduces its income. And that might either be nominal income or real income. We're going to be most interested in real income as a measure of sort of welfare exposure. So how dependent is my welfare to growth in China? And we're going to see how to compute that in a rigorous way in a class of general equilibrium trade models. Obviously, another challenge here is when you think about that question of as a country becomes more economically dependent on a trade partner, does it realign politically? Well, another kind of challenge I'm sure you're all thinking about is obviously causality as well, right? So it could be that as I become economically dependent on a country, I politically align with it, but causality could run the other way. Maybe for some exogenous reason, there's a political salience between our two countries, and that leads us to trade more with one another. And so obviously reverse causality, or more generally emitted variables that might both affect trade flows and political alignment are going to be a cause for concern. And so that's also something we're going to try to take seriously. And we're going to try to use the model to help us construct instruments. So we're going to be using kind of ideas of model-based instruments to also try to help overcome that challenge. Okay. How are we going to measure political alignment? Well, we're going to use a bunch of measures. We're going to use voting in the United Nations. Do countries vote in similar ways in the United Nations? We're going to use various different ways of coding that. We'll also use measures of strategic rivalries, which is where political scientists directly measure whether they think one country is a source of threats or an explicit enemy of another or engaged in conflict with another. And then we'll also use direct measures of formal alliances. So have we signed an agreement? What type of agreement have we signed with one another? And to try to use those and to try to see whether our results are robust across different ways of measuring political alignment. Okay, so more formally, how are we going to model this? Well, we're going to think about countries being able to undertake political actions that raise the productivity of their trade partners, but that incur utility costs. So I can vote in a way that's favorable to your economic development in the United Nations, or I can agree to a treaty that's beneficial for your economic development. That incurs some private utility costs to me. And so why am I going to be willing to do that? Well, I'm going to be willing to do that if adopting this favorable policy to you that raises your growth enhances my welfare. And so countries are essentially going to trade off the private utility costs of undertaking favorable political actions against the economic gains from taking that action, raising the growth in their trade partner, and thereby increasing their own welfare. I'm going to use a trade model to measure that economic dependence, the impact of growth on my welfare. Okay. So what are we going to use for the two instruments I mentioned to overcome the challenge of endogeneity? Well, we're going to use two different sources of quasi-experimental variation. So the idea here is if we find similar results with two very different sources of quasi-experimental variation, then other things equal, that might enhance the credibility of the empirical findings, because those instruments are using very different sources of variation in the data. So we use a model-based instrument based on China's emergence into the global economy, so building on the idea Otto Dorn Hansen and many others in the trade literature have explored, that China's domestic reforms in 1978 were a shock to other countries because they enhanced its growth, led to an expansion in trade, and that then impacted other countries. So that's going to be our first instrument, derived within the structure of the model, and I'll explain that a little bit later. And then our second instrument, we're going to use an idea from James Fira, from a second paper by James Fira, which is that over time, the share of trade by air has increased dramatically. So anybody know what share of, if you exclude Canada and Mexico, anybody have a guess what share of US imports is by air, by value? Anyone have any sense? What, 2%? 80%? Anyone want to hazard a guess? 50%, which is pretty amazing, right? That's by value rather than by weight. So by weight, obviously, most stuff comes by ship. But by value, if you exclude Canada and Mexico, around 50% of US imports comes by air. And if you go all the way back to the 60s, and even before the early days of jet travel, that share of air shipments was obviously much, much smaller than today. And so what's the idea? Well, the invention of the long-distance aeroplane reduced trade costs differentially for countries that have long sea distances relative to air distances. So if you look at the position of the land masses on the globe, they generate a lot of variation in sea distances because ships have to sail around the coasts to go from one port to another. And so when there's a new innovation like air travel, where I can fly great circle distances, essentially I can fly point to point, follow least cost paths, that's going to unevenly reduce trade costs depending upon the extent to which countries have long sea distances relative to their straight line or great circle air distances. And so that'll be our second source of variation. Okay. What do we find? Well, we find that increases in my economic dependence on a trade partner predicted by our instruments indeed lean towards political realignment. We find that's very similar estimates across these two very different sources of quasi-experimental variation. And we find that using our theory-based measures of economic exposure is kind of consequential. If we just use a simpler measure, like bilateral trade, we do not find the same thing. So actually using the model and the models-based measure is sort of informative. Okay, cool. So then obviously, this connects with a rich literature on international political economy and recent work on geoeconomics, including Matteo and Antonio and Chris's work, about which they're going to be talking later as part of this course. So how are we going to measure this general equilibrium measure of economic dependence? Well, we're going to take the standard class of constant elasticity trade models. So, I'm sure many of you are aware, in international trade, there's now a whole class of models. What defines this class of models? Well, essentially, they all imply a gravity equation for trade flows, in which there's a constant elasticity of trade flows with respect to trade costs. Okay, and I'm going to develop one of those models here, which is perhaps the simplest model in that class, and that's the so-called Armington model of trade, where goods are differentiated by country of origin. So in other words, German goods are different from French goods. They're horizontally differentiated from one another. But within Germany, markets are competitive. Many firms can produce the German good. One unit of the German good is the same as any other unit of the German good, but it's just the German good is different from the French good. And that seems like a very bare bones model of trade. It's actually a model quite often used in international macro, so it's kind of nice to see it in terms of bridging the gaps in international macro. Macro often works with Armington models. But essentially, there's no loss of generality here, because instead of this Armington model of trade, we can derive exactly the same predictions from the Eaton-Kortum 2002 Ricardian model of trade, in which trade is driven by technology differences across goods and across countries. As long as technology is random and drawn from an extreme value distribution, a fresh air distribution, that's going to give us exactly the same system of general equilibrium conditions that I'm going to outline in a second. So that's another model in the class. So Armington, goods are differentiated by origin. Ricardian model, technology drives trade. What's another model within this class? Krugman 1980. So the Krugman 1980 model, in which firms make differentiated varieties under conditions of monopolistic competition and increasing returns to scale. It turns out that that model also falls within this class. And a fourth example of a model within this class, the Melitz 2003 model of firm heterogeneity in differentiated product markets. If productivity is Pareto distributed, then again, it's going to fall within this class of constant elasticity trade models. Why are we so obsessed with this class of constant elasticity trade models? Well, in particular, it does a good job at hitting one key moment in the data. It explains why the gravity equation is extremely high predictive power for bilateral trade flows. So in other words, if you regress bilateral trade between countries on exporter fixed effects, importer fixed effects, and just geographic distance, so something incredibly simple, you'd think it's too simple to have much explanatory power. In logs, that has an R squared of around 0.8, a lot of predictive power. If you estimate it with something more sophisticated, like a Poisson pseudo-maximum likelihood estimator to allow for zeros, that also provides a good approximation to the data. And so this sort of constant elasticity relationship is obviously not going to be perfect, but it's going to provide a good approximation to the data, and that's why this class of models is so widely used. And so we're going to take that widely used class and show it how you can derive this rigorous measure of the extent to which my welfare is dependent on growth in a trade partner. So let's walk through that. So what's our assumption about preferences? Well, we're going to think about countries' preferences are defined over these horizontally differentiated goods produced by each nation around the world. And they're going to take the constant elasticity of substitution for. Okay, and so I've written here the indirect utility function. So the utility function in terms of wages and prices. So the wage in the numerator, and the denominator is the ideal price index. It's the cost of living for a constant elasticity of substitution demand system. So I'm just summing, this is utility in country N, summing across all exporters I. So that's important. I'm using the Eaton-Kortum or Kostas-Arkalakis notation. The first subscript is the importer. The second subscript is the exporter. Okay, so the price index depends upon the sum across all exporters of the price they charge to importer N raised to a power. And that power is 1 minus sigma, where sigma is the elasticity of substitution between these countries' goods. And I've just defined theta as sigma minus 1, and then written the price index where the exponent on prices is minus theta. And the reason I've done that is going to be obvious in a second, because theta is going to be the trade elasticity. The elasticity of trade flows with respect to trade costs is going to depend upon sigma minus 1. Okay. So what's the feature of the CES demand system? Well, as we know, it gives us these nice constant elasticity expressions for expenditure shares. They take the sort of logit or CES form, where the expenditure share S of importer N on exporter I depends upon the price that exporter I charges in market N relative to the price charged by all other exporters, okay, where the prices are raised to a constant elasticity. Okay? So, strong assumptions for those of you interested in IO at all. If anybody here's on the IO, International Macro Boundary, which may be a small set, but the strong assumption here is independence of the relative alternatives. So if I look at relative expenditure shares for two exporters, it just depends upon relative prices, not upon the price of any third other country. Okay. How about the production side of the model? Well, simplest possible production slide. Goods are produced with labor. So W is the wage. Linear production technology, constant returns to scale. We're going to allow our countries to differ in terms of their productivity, Z. And countries are going to face iceberg bilateral costs of trade. So if I want to ship from country I to importer N, I have to ship tau Ni units of a good in order for 1 unit to arrive. Okay, so tau is a measure of the iceberg. So tau minus 1 melts in transit. I ship tau greater than 1 unit, and 1 unit arrives. Okay. And so if I substitute that pricing rule into my expenditure share, now I see immediately this constant elasticity gravity equation. Bilateral expenditure shares, the share of expenditure of country N on country I, depends upon bilateral trade costs, tau Ni. And so if I think trade costs increase with distance, that's going to be what explains in the data that I see distance declines, trade flows decline with distance, roughly with a constant elasticity. Okay, but we also see some another very important insight of the model, which is that it's not just bilateral trade costs that matter for the trade between importer N and exporter I. Importer N's trade costs with all other exporters, M, also matter because they're in the denominator here. If I substitute for P and M using my pricing rule, I see that it's not just bilateral trade costs between N and I that matter for their trade, it's also multilateral trade costs or multilateral resistance, the trade costs with all other nations. So in other words, Australia and New Zealand, they're a long way away from one another, but they trade much more with one another than you think based on their distance. Why? Because they're miles away from anywhere else. Okay? And so it's my relative prices that matter for trade flows, and that's one of the key insights of these models, what's called structural gravity, that you need to take account of those price index effects. Okay? And so what's so elegant about this class of models is that the general equilibrium of these models reduces down to a single system of equations for the N countries, so the system's defined across the N countries, and the only unknown is going to be the wage, or the only kind of key endogenous variable is going to be the wage in each country. Okay? And so what does this system of equations equate? It says that income in each country of production, which is paid out to labor with zero profits, so the wage times the labor endowment, income in country I has to equal expenditure on the goods produced by country I. So that's just the sum across all markets N of income in each market multiplied by the share of expenditure the market N spends on I. Okay? And if we substitute our expression for shares into that income accounting equation, and if we substitute for the pricing rule in prices, we're going to see that we can reduce that system of equations down to a system in the vector of wages in each country around the world. And so the actual only unknowns in this general equilibrium system are the wages in each country around the world. I'll say more about that in a moment. When I'm going to be sort of solving for the impact of productivity shocks, I'm going to need to pick a numeraire. I'll typically pick the numeraire that world GDP is equal to 1. And just for sort of future reference, I'm going to define Q as income, so wages times the labor endowment. And so the sum of Q across all countries around the world equals 1 is going to be my choice of numeraire, and you'll see why that's convenient in a second. Okay, so now let's look a little bit more about that general equilibrium. So now I've made the substitution. We see the system of equations and the N wages in each country. And what's nice about this system of equations is it's really just an excess demand system, right? Well, what is the demand here? It's the demand for country's labor. And the price here is the wage, the price of labor in each country around the world. And this excess demand system satisfies gross substitutes. So if I increase the price of the good produced by country I, that's going to reduce expenditure on country I and increase expenditure on everybody else. And if I increase the prices of any other country's good, that's going to raise expenditure on the good produced by country I. Okay, and so we know that the system is going to have a unique equilibrium wage vector that's going to satisfy that system of equations. So the equilibrium in the model is unique. Okay. Now, when we're interested in this question of economic dependence, how much does my welfare depend upon growth in other countries? I'm now wanting to think about a general equilibrium experiment. I'm going to say, I'm going to look at the system of equations and I want to answer the following question. If China's productivity increases, so if Z goes up in China, what is the impact of that on my wage, firstly, on my nominal income? And then what is the effect of that on my welfare? And so how would we typically do that in trade? Well, the standard approach to solving for a counterfactual like that, so what happens if there's a shock to China's productivity? What does the model imply will be the effect on wages and real income? Well, the state-of-the-art way of doing that will be the so-called exact algebra counterfactuals introduced by Decker-Leeton and Kortum, are widely used in trade now. So for those of you who don't do trade as much, this may be a little bit less familiar, but I think it's also diffusing in macro as well. What's so beautiful about this way of doing counterfactuals? Well, let's think about an initial equilibrium and a counterfactual equilibrium. And let's denote a variable in the counterfactual equilibrium by a prime. So x prime will be the value of x in the counterfactual equilibrium. And let's denote the value of a variable in the initial equilibrium by x, where typically we see the initial equilibrium in the data, it's observed. And then let's define a relative change of a variable between the counterfactual and the initial equilibrium by a hat. So x hat is just equal to x prime divided by x. It's just the relative change in the variable between the counterfactual and the initial equilibrium. Well, why is that notation useful? Well, if I go to my general equilibrium system of equations, and imagine that system of equations at the top of the page, but for the counterfactual equilibrium. So write a prime for the endogenous wages on all the endogenous wages. And I know all the parameters of the model potentially could change as well, so prime on every variable in that system. And now let's rewrite that system of equations, all written with primes on every variable, in the following form down here. Well, look on the left-hand side of the equation, I've got W prime L prime. Well, just as an accounting identity, I can rewrite that as W times L times W hat L hat. Why? Because W hat L hat is the primes divided by no prime. So I've got primes divided by no prime, the no prime cancel, and I'm back with the prime. Right? And so I'm just taking the counterfactual system of equations written with the prime, but I'm just rewriting it in an equivalent form as an accounting identity so that I can rewrite the entire system simply using initial values of variables that I see in the data. That's the key advantage of this, is I see the initial equilibrium, and the relative values, which are the things I don't see, things I want to solve for, relative changes in the counterfactual equilibrium. And then I've done exactly the same thing on the right-hand side, and I've done exactly the same thing in the expenditure shares as well. And when I do that, what's nice is when I write the hat terms and then I've got the terms without the hats, I can replace those terms without the hats by the observed expenditure shares. Okay? And so what's so beautiful about this is I want to solve for the impact of a productivity shock, a change in Z, on the endogenous wages. And by rewriting that system of equations in the counterfactual equilibrium in the way, I can answer that question without knowing anything about the initial level of productivity in any country around the world, and without knowing anything about the value of trade costs, bilateral trade costs between each country around the world. Why? Because they're absorbed in the observed expenditure shares. They're capturing the trade costs and also embodied productivities, and then the observed wages also affected by productivities are also embodied in those observed wages. And so essentially I'm eliminating the things I don't observe and replacing them with endogenous variables I observe in that initial equilibrium. And then if I hold the endowment constant, then L hat will be 1, and I'm holding trade cost constant, so the only thing I'm changing is productivity here. Well, now I've got a system of equations where I'm feeding in an assumed change in productivity, so that's something I know. Everything else is observed, and I can just solve that system for the W hats, the unobserved changes in wages. And so I'm able to solve for a counterfactual just using the observed values of variables in initial equilibrium. Okay, so very, very powerful, widely used in trade because it avoids having to estimate all those unobserved fundamentals. Yeah?
Yes, so the interpretation of that is dependent on the numerator that you choose, which is like the world GDP. So let's say, like if you say wage goes up, you're actually saying wage as a percentage of GDP is going up. but we know nothing about the world GDP, how the productivity shock is changing.
It's a great question. So you're ahead of me out, something I was going to say next, and you'll see that's going to be coming up on a later slide. So let's look at that question. Let's look at the system of equations. What do we notice about this system of equations? So I'm going to restate your question in a different way. This system of equations is homogeneous at degree 0 in the relative changes in wages. In other words, imagine I multiply both sides of the equation. I multiply all the relative wages by some multiplicative scalar lambda. Okay, well, the lambdas are going to cancel from the numerator and denominator. The lambda is going to cancel over here and over here. And so that system of equations is homogeneous at degree 0 in wages. So absolutely, to recover a particular value of wages, I need to impose that numeraire. That's why I've imposed it earlier, and I'll say more about that in a second. But the relative value of wages can be uniquely determined from the system of equations. Why? Because we know the system has a unique equilibrium. So up to a normalization or a choice of numeraire, we can pin down relative wages uniquely. Yeah, it's a great question. So if I want to now ask my question, how dependent is my welfare on growth in each country, I know exactly how to do it. I can just feed in those assumed changes in productivity in every country, solve that system of equations for wages. And the top slide there, I've just rewritten that system of equations in a slightly different way. And you'll see in a second why I've done that. So what have I done? In particular, I've taken these terms in W and Zi outside the summation because they don't depend on N. And I've defined a new variable I've called T. And what is TIN here? TIN is the share of country I's income that comes from market N. So it's an income share instead of an expenditure share. It depends on the expenditure shares, income in market N divided by income in exporter I. So I've just defined that T there. And then I've just taken the terms in I outside the summation, taken the power over to the left-hand side, and then raised the whole thing to that power on the right-hand side. And I've just rewritten it in an equivalent form. And you'll see why I've done that in a second. And then I've now also written the change in welfare. And what's that change in welfare? Well, that's just the change in wages relative to the change in the cost of living. And again, I can rewrite that using my hat algebra. In terms of relative changes in the endogenous wages, the exogenous productivity I'm feeding in, and then the initial expenditure shares in the initial equilibrium. Okay? And so one feature, again, related to that question, the change in welfare is not going to depend on that choice of numeraire, right? Because we mentioned earlier, we can only pin down wages up to some multiplicative scalar, but the multiplicative scalar here will net out between the numerator and the denominator in welfare. And so welfare is actually uniquely pinned down regardless of the numeraire. Okay, and so now I'm kind of in business. I know how to solve for how does growth in a country such as China, how does that affect my nominal income up to my choice of numeraire, and how does it affect my welfare? Okay. What's the limitation about this exact hat approach? Well, when I'm thinking about how dependent is my growth on China and I want to solve this system of equations, I have to assume something about how big the productivity shock is in China, right? I have to assume a size for Z hat, the change in productivity shock. And I have to do this counterfactual n times for every single country around the world. I have to say what happens if China's productivity increases, solve for the GE, then say what happens if productivity in Malaysia increases, do the GE. But I can do that, and I can sort of calculate a whole set of arc elasticities. What's the log change in my welfare divided by the log change in productivity from a productivity shock? And that's going to tell me how sensitive is my welfare to a productivity shock in each country around the world. So I do that n times, my n countries, and I'm going to be able to populate a matrix. How dependent is the welfare of every country in the world? So those are the rows of the matrix. And then the columns of the matrix are I'm shocking productivity in each country around the world. Okay, so I shock China once, and I get a prediction for the change in the welfare of every country around the world. That's a vector. And then I shock every other country. I'm adding in an extra vector until I populate the whole matrix. Okay, limitation is I have to assume a size of a shock, and I'm effectively computing an arc elasticity, a sensitivity of welfare for an assumed size of the shock. Yeah.
So would you also worry about something like the cross elasticities not being identical? So like with the Armington trade model, you have all the cross elasticities are identical. Mm-hmm. So if you worry about something like, oh, China is very substitutable with some countries, but not other countries.
Yep, so great question. So let's restate that question another way. So it's related to what I said earlier about the independence of the relative alternatives. So the independence of relative alternatives says that the relative expenditure shares for two countries, US expenditure share on India and China, just depends on their relative prices. It doesn't depend upon the price of Afghanistan or any other third country. Closely related implication of that is that the CS demand system imposes very strong cross-substitution restrictions. When China's price goes up, what does the CS demand system say happens to all other countries? Well, it's going to depend upon the elasticity parameter, the theta, the trade elasticity here, and it's going to depend on the initial expenditure shares. And everything is going to be symmetric depending upon the trade elasticity and the initial expenditure shares. And that is for sure a limitation of this constant elasticity class of trade models. And you'll see the exact cross-substitution effects. I'm going to delve into them in a little bit more detail in a couple of slides. So yeah, great question. So, there is some work trying to relax this constant elasticity assumption. So, for example, Kostas Arkalakis and Sharat Ganapati have a paper where they try to estimate this demand system non-parametrically using the techniques of Berry and Hale from the IO literature. I have a kind of a theoretical paper with Mark Mellitz where we kind of make that point that if the trade elasticity is variable, it matters for the impact of shocks such as trade costs on welfare. And it can substantially change the welfare predictions of these models if you have a variable elasticity rather than a constant elasticity. Yeah, great question. Cool. So that would be the standard way of doing this. We're in kind of trade using exact algebra. One of the things we've been sort of popularizing in some of our work is that there's also another way of thinking about these questions, which is that to do something that's very common in macro and international macro, and that's to linearize the general equilibrium system of the model. Okay. So what are we going to do? Well, we're going to start with that exact same income equation here at the top of the page, and we're just going to totally differentiate that system. Okay. And that's exactly what we've got at the top of this slide here. I've just totally differentiated that system of equations, so taking the total derivative dw, and then dividing through by w, writing everything as dw over w, which is d log w, and just doing a standard linearization that we do in macro all of the time. And then what have I got on the right-hand side of the equation? Well, you'll see that I've actually got something that looks remarkably similar to the exact algebra. I've got the things that are endogenous, so the changes in wages. So now I've got d logs instead of w hats. The exogenous thing I'm feeding in are the dz's. They're the productivity shocks. They're on the right-hand side. And then I've got my single parameter, the trade elasticity. And then I've got the initial expenditure shares, the little s's, and the variable I define, the income share, little t. Remember, little t is the share of income that country I gets from market N. Okay. And if you go back to this slide, you actually see that when I rewrote the nonlinear system in this way, it's actually remarkably similar to the linearized model. It's just here I have a log of a weighted mean, where the weights are the income shares. Whereas in the linearized model, I have a weighted mean of the logs, the change in the logs. Right? And so these things are very kind of closely related to one another because this is a constant elasticity system. Okay? So I've just totally differentiated that income equals expenditure equation, and then obviously I can do the same for welfare. Take the total derivative, it's just the change in wages, and then it's going to be the expenditure share weighted average of the change in wages and the change in productivities. That's the usual first order approximation for the change in the cost of living with respect to a change in the price of a good. Okay, and again, very similar to the expression in the nonlinear model, except I've got logs of a weighted sum versus a weighted sum of logs. Okay. So what's nice about this linearization is it actually gives you a lot of intuition for what's going on in this general equilibrium system when there is something like productivity growth in China. So we can see that if we sort of relabel some of these terms. So what I've done now is I've rewritten that system of equations in matrix form. Okay. So I'm totally differentiating the whole system. So on the left-hand side, I've got the change in the wage of every individual country. I'm going to stack them in a vector of the d-log changes. So the bold font here is a vector. And then I'm going to stack everything on the right-hand side. So I can write those sums in terms of the t's times the d-log w's. I can write that as the matrix of income shares times the vector of changes in wages. That's just rewriting the sum in matrix form. And then I can rewrite those terms in the product of the t's and the s's. That summation, I can again write it in a matrix form where I've got a scalar, theta, and then I've got another matrix m times d log w minus d log c, where again, those are both vectors. And this matrix M, related to Oliver's question, is the cross-substitution matrix. Okay, so and let's sort of talk through that intuition. Well, what happens when China becomes more productive? Well, that's going to affect wages in every country around the world. So wages in each country around the world are going to change in general equilibrium. And that's going to affect my income on the left-hand side. How much is a change in wages in any market going to affect my income? Well, that depends upon what share of my income I get from that market. So this first term here is essentially a market size effect. And when there's a change in productivity, there's a G effect on wages in every country around the world. That changes market size around the world, and that affects my income. And then the second term here is exactly this cross-substitution effect that Oliver was thinking about. When China becomes more productive, what does that do in every market around the world? Well, in the German market, Chinese goods are now cheaper. And so I'm going to sell less of my goods in the German market because I now face a tougher competitor. Chinese goods have become cheaper. What does CES demand system say determines that cross-substitution? It depends critically on the expenditure shares and the single constant elasticity theta, right? And so as China gets more productive in the German market, I lose some expenditure in that market. How much do I lose? It depends on expenditure shares. How much does that loss in expenditure affect my income? Well, it depends upon the income share I get from the German market. And that's why the cross-substitution here is the product of the income share and the expenditure share. Okay. So it's just rewriting that system of equation in matrix form, and in the linearized model, you get this kind of clear understanding of why a country could be a friend or an enemy in economic terms. So when China becomes more productive, that could either increase or reduce my wage. Why? Because it depends upon how market size changes around the world and the share of my income I get from each of those markets. And it depends upon these cross-substitution effects. My income could go down if I compete heavily with China. If I get a big share of my income in markets where China accounts for a large share of expenditure. That's where I'm going to be really hurt by growing Chinese productivity. Okay. And then again, I can stack the real income exposure equation in matrix form, where I've got the vector of changes in welfare, the vector of changes in income, and that vector of changes in the cost of living. What's the advantage of this linearized model, and what's the disadvantage? Well, the disadvantage is obviously a first-order approximation. I'm linearizing, right? And so for large changes, the worry might be we don't know how good that approximation is going to be, and I'll show you some evidence on what that looks like, the approximation error. What's the advantage? Well, the advantage is that we can actually, instead of having to do n separate counterfactuals, so what happens when I shock productivity in China to the welfare of every country in the world, then I shock productivity in Ghana, I shock productivity in Brazil, and so on, and I have to do n counterfactuals in the exact algebra approach. Here, I can recover that whole matrix of exposure from a single matrix inversion. Okay? So in particular, what am I going to do? I'm just going to take all the wages over to the left-hand side of this equation. I'm going to take a matrix inverse, and then I'm going to be able to recover the whole matrix of bilateral exposure from a single matrix inversion problem. Okay, and this is where our choice of numeraire is going to be important, because obviously we can only determine wages up to the numeraire. So in order for that matrix to be invertible, I'm going to have to impose that choice of numeraire. Why? Because the expenditure shares sum to 1. So the rows and columns of the matrix are not all going to be linearly independent unless I impose a choice of numeraire. Okay. So that's what we've done here. We're just going to impose our choice of numeraire. So all I've done in the top line, I'm just rearranging that wage equation, just dividing through by theta plus 1. Then I'm just taking all the terms in wages over to the left-hand side. We can write that as the identity matrix minus t minus theta m. Okay, taking the terms in t and theta m from the right-hand side to the left-hand side. I'm now going to define that cross-substitution matrix M as Ts minus I. So that enables me to rewrite it in the line below. And then I've just rewritten it in a slightly more parsimonious form there. And then finally, I need to, in order for this to be invertible, so this here is not invertible because the expenditure shares and the income shares sum to 1. So in order for that to obtain invertibility, I need to impose my choice of numeraire. Remember I said that my choice is that the sum of the q's is equal to 1. Well, that means the sum of the q's times d log w has to be equal to 0. Okay, just taking the log total derivatives in that choice of numeraire. And I can rewrite that sum of the q's times the d log wages equals to 0 as just the product of a matrix Q, which has rows equal to that income vector. So it's just populated with rows equal to that income vector multiplied by d log W. Okay, and so that's how I'm going to impose my choice of numeraire. So I'm just adding this term in on the left-hand side because under my numeraire, I know that term is equal to 0, so it doesn't change the left-hand side at all. And so now I can just invert that equation, and I'm going to recover what we call the friends and enemies matrix. So W here is that term I just derived, theta over theta plus 1, I minus V inverse, where V are those terms in T and T times S from the previous slide. Okay, and then what is my welfare exposure? Well, once I've inverted the model and I've got the W matrix, welfare exposure is just the identity matrix minus the matrix of expenditure shares times the W matrix plus the matrix of expenditure shares. And so I can just do a single matrix inversion. It takes fractions of seconds on a modern computer, and I get a whole matrix of exposure for the whole world. Okay, so that's particularly powerful if you want to do a large number of counterfactuals. It also gives you point elasticities, right? Because I'm looking at small changes here, so I'm getting exactly how sensitive is my welfare to changes in productivity in China. I don't have to pick a size of the productivity shock as I did in the exactly algebra. And I no longer get an arc elasticity, I get a point elasticity. Okay. So that's kind of an alternative way of thinking about constant elasticity trade models, just using standard linearization techniques. What are the insights you get? Well, you understand the kind of mechanisms, the market size effect, the cross-substitution effect, and you get this ability to just invert the model and get the full matrix of welfare exposure to productivity growth in every country around the world as a single matrix inversion. Just to sort of flag, obviously, I'm illustrating this in the sort of standard class of trade models where we have a single sector model with a constant trade elasticity. But this methodology is actually much more general. So we show in the paper a very similar representation holds in a multi-industry model without input-output linkages like Costno, Donaldson, and Kamunja, for those of you who are familiar with that paper, or a multi-sector Armington model, same representation holds. Same representation holds also in the Caliendo-Paro paper I mentioned earlier. You can rewrite everything in this matrix form. The only thing that changes is you have to change these expenditure share matrices and income matrices and cross-substitution matrices. Why? Because in a country industry model, the US competes with China in the textiles market in Germany, right? So it's the market industry where I'm competing, and the expenditure shares and the income shares could be different in different industries. China could be a very strong competitor in Germany in textiles in the sense it accounts for most of the market, but it might be a weak competitor in Germany in another sector. Yeah.
But this matrix is still of first order in some sense, right? It only captures the direct effects and not the fact that, for instance, if China productivity increases, it increases productivity in Mexico, and that affects the US.
It's a great question, so let's think about that. So you're absolutely right that this matrix inversion is first order, so it only captures first order effects, but it does capture first order GE effects. So it captures the full GE feedback because essentially we're solving this entire system of equations but just the first order terms. So it does have some GE feedback, so we're taking account when China's productivity goes up, wages in Germany might change, and that affects my wage as well. So we're taking those into account, but we're abstracting from the second order and higher terms, and as you pointed out, we're treating the productivity of every other country as fixed. So we're not thinking about knowledge spillovers or endogenous technology. But it does capture first order GE effects in this class of models. Cool. So in the multi-industry model, we have to think about competitions in an industry, and expenditure shares and income shares may vary. And then obviously when we have input-output linkages, we have to take account of the fact that if I'm using Chinese goods as an input, higher productivity in China might not be good for me because it lowers my input prices. So we need to take account of the full value chain, the full structure of the global value chain. But again, in the Caliendo-Paro model, which assumes like a Cobb-Douglas input-output structure, we get exactly the same representation. We just have to construct the S, T, and M matrices in the right ways. What do they depend on? Well, they depend upon observed things like expenditure shares, cost shares, and trade elasticity as before, but also the Cobb-Douglas shares in the input-output table are going to matter in the construction of those matrices. Cool. So let me sort of illustrate this first application, show you what we found very quickly. and then talk about how we can combine these constant velocity trade models, use these linearization techniques, but bring them together with an international macro model where we have both trade and capital flows. So we're going to use some of the comp trade database I mentioned. We pull the CEPI gravity to get us income, population, and distance. And then we are going to measure political alignment using United Nations voting, strategic rivalries measured by political scientists, and measures of formal alliances. We're going to use a sort of technique that's pretty common in trade to get measures of trade costs. We're going to invert the equilibrium conditions of the model. So we're going to recover bilateral trade costs from what's known as the head-Reese index. So that's noticing that we want to find out trade costs to feed in as shocks into our model, but we don't directly see them, as I mentioned earlier. But if we observe bilateral exports, so exports of importer N from exporter I, relative to importer N's trade with itself. And then we also observe the mirror flow of that, XINT, relative to I's trade with itself. So if you compute those ratios, raise them to the power, then on the right-hand side, everything cancels. All the exporter fixed effects are differenced out, and all the price indices terms, all the denominators cancel out, again, because of the double differencing. So it's a kind of trick often used in trade. If you take that double difference, you eliminate the exporter characteristics and you eliminate the importer characteristics, and the only thing you're left with is the bilateral characteristics. And if you're willing to believe trade costs are symmetric and you normalize your trade costs with yourself to 1, then you're going to recover bilateral trade costs between the two countries up to that assumption of symmetric trade costs. So we're going to just use that to get a sense as to what would be an empirically plausible set of trade cost shocks to feed into the model. And once we've got our trade costs, we then back out productivities, again up to a normalization because it's homogeneous at degree 0 from this income accounting relationship to get to back out from the data an empirical distribution of productivities to feed into the model as shocks. And then related to questions earlier about how good is the approximation, so we actually find for productivity shocks, the first order approximation in these models is extremely good. So essentially here we're reporting sort of Monte Carlo evidence where we're going to feed into the exacted algebra a set of productivity shocks. And what productivity shocks are we going to choose? Well, we're going to choose a weighted average of the empirical change in productivity between 1970 and 2012, backed out from our model inversion. So that's a big number because it's a productivity change over more than 40 years. So that's going to be the extreme when we have a weight of 1 on those empirical shocks. And then the other extreme is we're going to have a vector of 1s. And so we're going to place a weight of 0 on the empirical productivity shock and a weight of 1 on the vector of 1s, in which case there are no shocks because the relative change in productivity, z hat, is equal to 1 for every country around the world. And then we're going to report everything in between, all the weights in between, placing 1 on the empirical vector of productivity shocks and placing 0 on it and a weight of 1 on a vector of 1s. And what do we find? Well, we find for productivity shocks on the vertical axis, I'm reporting the correlation between the predictions of our linearization for log changes in welfare and the predictions of the exacted algebra counterfactuals. And you can see for productivity shocks, they're almost exactly the same, correlation very close to 1. For trade cost shocks, the correlation is less good. And as we place a weight of 1 on the empirical changes in trade costs, we get down to some lower correlations. That makes a lot of sense because let's think about what the second order terms are that we're omitting from this linearization. Well, they're terms in the changes in the shares times the changes in the productivity shock. Those are the second order terms. If you think about a shift in productivity, it's an exporter characteristic that's common across all importers trading with that, right? And so it's something that sort of differences out across some of your bilateral pairs. And so productivity shocks don't lead to as big changes in shares as bilateral trade costs, because bilateral trade costs are bilateral. They only affect one partner and hence lead to a larger adjustment in shares. And so that's sort of one intuition for why the first order approximation is better for productivity shocks than it is for trade cost shocks. But even for pretty big trade cost shocks, the approximation is pretty good. So this is a measure of global welfare exposure. So we've got our matrix now of how exposed is each country around the world to productivity growth in any other country. And this left panel here is showing average welfare exposure over time The right panel is showing the standard deviation of welfare exposure over time. And so we're computing this in every year based on the observed expenditure share and income share matrices in that year. And you can see a story of rising globalization, that over time, countries are now more exposed to one another as productivity growth, consistent with there being globalization during this period. And we also find that welfare exposure becomes more dispersed. Again, potentially consistent with growing globalization, and now there's sort of more heterogeneity in that welfare exposure between pairs of countries. We validate our welfare exposure measure by sort of showing that if you regress it on measures of countries signing free trade agreements, you'd expect welfare exposures to go up when you sign a free trade agreement because it lowers trade barriers between you. And so we report event study evidence in the paper showing that we find that measure of welfare exposure responds very strongly to this completely separate measure of trade agreements that we didn't use at all anywhere in how we computed welfare exposure, just as a kind of validation effect that we sort of really think we're capturing welfare exposure. And then because we've got this matrix of welfare exposure, we can sort of use measures from the networks literature that think about characteristics of that network. So what are the measures we're going to use here? We're going to use measures of authority score and hub score, which are sort of generalizations of notions of eigenvector centrality to the case when you have a directed network. So the authority score is going to capture how important is a country as a source of real income shocks for other countries. And the hub score is going to capture how important is a country, how sensitive is a country to productivity shocks in other countries. Right? So an authority means I have a big effect on other countries. Hub means I'm very affected by other countries. I'm very sensitive to other countries. Okay? And so those are those measures. And so once you give me the matrix of welfare exposure, I can compute those hub and authority scores for each nation around the world. And again, we see a sort of intuitive pattern. Here I've plotted the measure of authority score, how important is a country as a source of shocks to others, to the welfare of others. And unsurprisingly, you find Japan becomes much more important during its period of rapid growth in the 1970s and 1980s, and China becomes much more important as a source of shocks to others during the sort of 1990s and 2000. And those changes in authority scores are actually much bigger than the changes in relative GDP. So again, there's some extra insight from actually using the structure of the model and computing welfare exposure in the model consistent way. I want to make sure I have time to talk about the kind of international capital side. So I'm not going to spend a lot of time on the sort of evidence in the paper, but I'll just kind of show you one brief glimpse of it, and then you can sort of delve into the paper in further detail if you want to look at the sort of IV results and look through at each of the different IV specifications. So in the panel here, this is just sort of showing you some simple correlations. In the top panel, we've got welfare exposure to productivity growth by country. And on the left, we've got the values in 1980, and in the right, we've got the values in 2010. So 1980 is just after China's domestic liberalization in 1978, and then 2010 is at the end of our sample period. And you can see this dramatic increase in exposure, welfare exposure, as China grows, particularly in East Asia. And this is from the Caliendo-Paro input-output structure version of the model, so modeling all of the input-output linkages. So in Factory Asia, we see growing welfare exposure to China, and we also see a large increase in welfare exposure in sub-Saharan Africa, also to some degree in Oceania. And then in the bottom panel, we plot voting similarity to China in the United Nations General Assembly in 1980 and 2010. You can do that in different ways. It doesn't particularly matter which way you do it. This is the sort of most sophisticated measure we have available. And you see there's sort of a striking similarity in this increase in voting patterns with the increase in welfare exposure. And that's clearly only a correlation. And in the paper, we developed those two different IV strategies I mentioned to try to kind of make the argument this is actually kind of a causal relationship. Okay. So that's my first of the two projects I wanted to talk about to sort of illustrate how we can use these constant velocity trade models, use them as a way of computing welfare exposure, income exposure, and linearize these models to be able to compute those measures of general equilibrium linkages, that network of linkages in the world economy, as part of a single matrix inversion. What I want to do in the rest of the talk is now connect with some of the work on the Global Capital Allocation Project and connect with some of Antonio and Matteo's lectures as part of this week, and now show how we can combine this trade model with a standard macro model and try to develop a framework where we have linkages between countries in both goods markets and capital markets. Okay, so how are we going to do that? Well, we're going to take essentially the standard closed economy neoclassical model of growth, the Ramsey model, which is a benchmark for thinking about cross-country income dynamics in the macro literature. And we're going to blend it exactly with that constant elasticity trade model, which we know is a benchmark for thinking about trade linkages between countries. And we want to think about how this trade and capital model interact with one another. How does trade matter for growth? How does growth matter for the impact of trade shocks? And of course, one big limitation of the closed economy neoclassical Ramsey model is that each country is essentially in financial and trade autarky. There's no reason for trade, there's a single good, there's no borrowing or lending in the basic closed economy Ramsey model, so completely financial autarky, and countries have no reason to trade. So what we're also going to do is we're going to open up that model and allow for international capital holdings in order to try to be able to connect the model to the data that we observe from the GCAP on global capital holdings. And we're going to ask the question, how do the linkages in trade markets and the linkages in capital markets through those bilateral holdings change our understanding of the growth process and of the impact of trade shocks? So what we're going to try to do, we're going to try to develop a framework where we have intra-temporal goods trade. So just like the model we discussed, countries are going to be trading with one another at a point in time. We're going to have intra-temporal capital holdings. So countries are going to have bilateral holdings of capital, like we see in the GCAP data. And we're also going to have intertemporal consumption saving choices. Because obviously, just like in the Ramsey model, countries have to be accumulating, making decisions about saving and investment over time. And so we're going to have endogenous current accounts and sort of be modeling that explicitly. Okay, so what are we going to get out of this framework? Well, we're going to show that the resulting framework is going to be able to match a number of key features of the observed data. So we're going to make sense of the fact why we see a gravity equation for trade in goods. But then also, maybe less well known, but it's also another good description of the data, why we see a gravity equation for capital holdings as well. We're going to have determinant predictions for gross and net capital holdings. So the model is going to explain why gross holdings are much bigger than net capital holdings, as Antonio was discussing at the beginning of this morning. The model is also going to give us a way of thinking about the Lucas puzzle. Why does relatively little capital flow to capital-scarce countries? Which is puzzling in terms of the standard Ramsey model. At least standard open economy versions of that would imply that all the capital should flow between countries to equalize rates of returns, and that's not what we seem to see in the data. And the model is also going to explain why we see home bias in trade and capital flows. Why both trade and international capital holdings are disproportionately concentrated domestically relative to what you'd expect based on country size. And then finally, the model will also give us a nice way of thinking about the so-called Feldstein-Horioka puzzle, why domestic and saving and domestic investment are very highly correlated with one another. Okay. We'll show how we can sort of generalize those exact algebra techniques I was discussing in the first lecture, how they'll still work even in this dynamic model, where we've got dynamic capital accumulation and open economy portfolios of capital holdings. And we'll also show how we can use similar techniques to linearize the model. And now once we linearize it, we don't just characterize the G at a point in time, we can actually solve in closed form for the entire transition path. Closed form solution for the entire transition path of the economy over time. Okay. And because we've now got this framework that has both bilateral trade and bilateral capital holdings, as I said, we can kind of think about how trade influences growth, how growth influences trade, and we can ask questions like what will happen if China and the United States decouple, not only in goods markets, but also in capital markets. And how does the presence of capital market linkages affect the impact of a decoupling in goods markets? And again, we're obviously building on a vast literature here, including, importantly, the work by Matteo and colleagues here at the GCAP. So let me give you the quick model setup, and then we'll dive into a little more detail into the equations of the model, and then I'll try to give you the kind of key punchlines that we get from bringing these frameworks together. So we're going to think of a country, of economy, consisting of many countries around the world, just like in the trade model we saw. Time is going to be discrete and in x by t. Each country is going to supply a differentiated good that's produced using labor and capital under constant returns to scale. So again, we're going to be in an Armington model. But as I said earlier, everything we do here in the Armington model will hold in any constant elasticity trade model. So pick your favorite constant elasticity trade model, all the results will go through. Only difference is now we've got capital as an additional factor as well as labor. Markets are competitive. Goods can be traded subject to bilateral trade costs. There's a representative agent in each country who's endowed with a measure of labor, just like in the trade model we saw. But now, here's going to be the different component. At the beginning of period T, our representative agent in each country is going to inherit some initial stock of wealth, A, and she's now going to decide how much to save and how much to consume. So she can make choices about the accumulation of wealth over time. And she's also going to make decisions as to where to allocate her wealth. And so in particular, she can choose to allocate her wealth to every country around the world. So we're opening up the Ramsey model, allowing the representative agent to hold wealth in any country around the world, subject to capital market frictions and subject to some idiosyncratic shocks that I'm going to talk about more in a moment. So at the beginning of period T, she's going to choose her wealth allocation across countries and make her consumption and saving choices. And then at the beginning of period T+1, investment returns will be realized, depreciation will occur, and wealth will again be allocated across countries. Just flag one big simplification we're making relative to some work in international macro and international finance. The model we develop here is going to have no aggregate uncertainty. So we're going to be solving the model under perfect foresight. Okay, so we're not going to speak to the recent literature on international risk diversification. But nonetheless, even though we're abstracting from aggregate uncertainty and international risk diversification, we're going to sort of show that we can explain many of the observed features of capital holdings that I talked about earlier. Okay. And for those of you interested in aggregate uncertainty, we're doing some new work where we're actually trying to model aggregate uncertainty in these types of models. And so there's a initial draft of our paper on that topic on our web pages. Cool, but now let's dive into a little bit more details. So the consumption saving choice, we're just going to make it plain vanilla. We're going to take the standard consumption saving model from macro. So we're going to have a representative consumer, constant relative risk aversion preferences. So beta is the discount rate, size, and temporal elasticity of substitution. And then we're going to have our consumer maximizing her intertemporal utility subject to her period-by-period budget constraint. So the value of her consumption plus the value of her wealth next period is going to have to equal her labor income plus her income from existing stock of capital, net of depreciation. And the only thing that's non-standard in that period-by-period budget constraint is her stock of wealth, AN, is being held in every host country I, and I've got to sum up across those host countries. And notice the way I've written it, I've taken the rate of return on those holdings, which is V. I've taken that outside of the sum because in equilibrium it's going to be the same across all of the host countries. That's why I'm able to do that. And I'll prove that to you in a second. And so I can actually then just rewrite that period-by-period budget constraint in exactly the standard macro form, where calligraphic R here is the real gross return to investment. Okay. So we know how to solve that problem. What is the solution? Well, with constant relative risk aversion preferences, consumption is going to be a linear function of current period wealth, as for example in Angeletos 2007, where that linear function var sigma here is going to be determined recursively between each pair of periods, as down here. Okay, so in the special case of logarithmic utility, var sigma here would just be 1 minus beta. And you'd have a constant rate of consumption and a constant rate of saving out of wealth if preferences were log. But more generally, with CRA preferences, it's a linear function, but that linear term is not necessarily constant. Cool. So that's standard. What about the model of capital holdings? Well, this is now going to be different. And this is where we're actually going to be bringing some ideas from trade into international macro. So how are we going to think about that capital allocation decision? Well, we're going to think about our representative agent as having a continuous measure of units of wealth. And she's going to choose where to allocate each unit in that continuous measure. And for each of those units, she's going to get a vector of productivity shocks for how productive it is to invest that unit in each country around the world. And we're going to denote those by phi NIT. Okay? So she wakes up, she's got this continuous measure of wealth, she thinks for every unit, where shall I invest this? She looks around the world and she gets an idea for a productive investment in every country. Some of those ideas are going to be better than others. They're going to have a higher productivity draw, a higher fee. And what is she going to do? Well, she's obviously going to allocate each unit of her wealth to the country that offers the highest rate of return. So what is that rate of return? Well, that's going to depend upon the rental rate per effective unit of capital in host country I. It's going to depend upon her productivity draw for that host country I, so fee NIT, how good her idea was for that country I, or the number of effective units of capital she had once we adjust for the quality of the idea. And then in addition in the model, we're also going to allow some capital management costs. So kappa NIT, they're going to capture capital market frictions where it might be harder to manage capital abroad than it is to manage capital at home because of additional information, search, matching costs. Okay. So what are we going to assume about these idiosyncratic shocks? Well, for those of you coming from the trade side, you probably guessed already, we're going to assume extreme value distribution for those idiosyncratic shocks. So phi here is going to be drawn from a fresh A distribution up here. Epsilon is going to regulate the dispersion of those idiosyncratic shocks to the quality of ideas. And eta IT is going to be a scale parameter, which will determine on average how good are the quality of ideas for a particular host country I. So for example, US assets might be particularly good, so the US has got a high value of eta, it's got a high draw for the quality of ideas that you draw from. So what is the advantage of making that extreme value assumption for those idiosyncratic shocks? Well, it's going to give us two convenient properties that are going to keep the model tractable and help us connect with the data. First thing, again, from trade, you're all going to be familiar with, is it's going to give us a gravity equation for bilateral capital holdings. So B NIT is going to be the portfolio share. What share of the wealth does the representative agent in country N hold in host country I? Well, that's just going to depend upon relative rental rates, that relative value of that parameter for the quality of ideas in host country I, and bilateral capital market frictions. But just like we saw in the trade gravity equation, bilateral capital holdings between N and I don't just depend upon bilateral frictions, but also multilateral frictions, the value of the frictions with all other possible host countries where I could hold my capital. So the model is going to deliver gravity for capital holdings, which I think I've got the slide on that later, is a very good approximation to the observed data on capital holdings if you take the GCAP data which we're using. Or any data on capital holdings has that property. It's a very strong property of the capital data. What's the second convenient property? Well, another property of this fresh A extreme value distribution is that the expected return, and because these idiosyncratic shocks are idiosyncratic, they're going to integrate out, so the expected return will equal the realized return. Expected return conditional on investing in a country is going to be the same across all host countries in equilibrium. And in fact, we have this nice closed form solution for it down here. So the return on my investment, if I'm in country N, if I'm the investor in country N, is going to be the same across all host countries I. So different host countries can have different rental rates, and they're going to face upward sloping supply functions for capital, as we see in the gravity equation here. If I want to attract a bigger portfolio share from any investor country, I have to offer a higher rental rate. So I've got an upward sloping supply function for capital. So some countries can have higher rental rates than others, but the average return conditional on investing in a country has to be the same across all countries. How is that possible? Well, if a country has a high rental rate, it's going to attract investments with low realizations for these idiosyncratic shocks. And so there's a composition effect. It's going to attract investments with worse ideas, and with a fresh A extreme value distribution, that composition effect exactly offsets the impact of the higher rate of return or the lower capital market frictions. And that's a convenient property because it means there's just a single rate of return in the macro consumption saving decision. And that's what I used earlier, where I took that rate of return outside the summation. And so those two features of the model are going to mean that it stays extremely tractable. It's going to match the data and gives us a tractable way of opening up the Ramsey model and bringing trade in as well. Okay, what's the limitation? Hang on 1 second, I'll take a question. What's the limitation? Well, as I mentioned, no aggregate uncertainty here. Okay, so we're going to be able to match the capital data, but we're not going to be able to say things about changes in aggregate uncertainty and risk diversification. Just make a couple of points about that. You actually can derive this gravity equation for capital flows in a variety of ways. And in fact, there are some models of international risk diversification which would also give you a gravity equation that takes exactly the same form. And so this gravity prediction, just like in trade, we have some isomorphisms. If you're focused only on the gravity equation, there are also some isomorphisms. You can derive it from this model of investments we develop here. You can derive it from international risk diversification models like Colgan and Yogo. And there's several other possible microfoundations. But in general, those models will imply something else for the other equilibrium conditions of the model. And so what's nice about this microfoundation is it's going to enable us to hit the Penn-Walt tables data, the national accounts data. It's going to connect directly with physical capital data. And the rest of the model is going to stay very tractable, and we can use it to think about the interaction between trade and growth, which would be much more difficult in a model of international risk diversification. And then let me take a question.
Yeah, so here the state variable is the total wealth. So capital is not accumulated within each country across time, right?
So great question. So the state variable here in the system is going to be the measure of wealth in every investor country, so ANT. That vector will be the state variable, vector of wealth. And then as you pointed out, each country, there's also a stock of capital in each country, but that's not the same as wealth. Because I can own some of the capital in another country, they can own some of my capital. And so when we solve the model, the state variable will be the stock of wealth, and we show in the linearized model, the stock of capital is just a linear function of the stock of wealth. So once you solve for the stock of wealth, you can recover the stock of capital and all the other endogenous variables. Yeah, good question. Cool. How about the trade side of the model? Well, this is going to be super familiar because it's going to look exactly the same as the model we did in the first part of the lecture. So we've got Armington preferences across countries with the constant trade elasticity, standard trade gravity equation that we discussed in the first part. Only difference here is that goods are produced with labor and capital. So we've got the wage to the power of the labor share. So we're going to assume a Cobb-Douglas technology, rental rate on capital to the power of the 1 minus the labor share. And then again, ZIT is our measure of productivity in country I. One thing we have to be careful of in the general equilibrium equations, we have to do all the accounting right. And so in particular, payments to capital at the point of production, so the rental rate times the capital stock, which with the Cobb-Douglas technology is just a multiple of payments to labor. It's a property of a Cobb-Douglas technology. So payments to capital at the point of production, they're going to have to equal the income received by everybody who owns capital that's used in production in country I. So income payments to capital used in country I has to equal the sum across investor countries of the amount they're investing in country I multiplied by their expected return, which, as we mentioned earlier, is common across all those countries, but differs across investor countries. Okay, and when we do that calculation, one thing we need to take account of is that the productivity of capital is going to depend upon those efficiency draws. It's going to depend upon the average efficiency draw conditional on investing in a country. And another nice feature of the Frechet extreme value distribution is that we have a closed form solution for what is the average productivity of capital conditional on investing in a country. It's just a constant elasticity function of the share of my portfolio I invest there. So in some ways, this model is actually reminiscent of sort of Keynes's idea of a diminishing marginal efficiency of investment schedule. If I invest more of my portfolio in a country, I'm moving down to worse and worse ideas, and there's lower and lower productivity of those investments. And this is the sort of micro foundation of that idea using an extreme value distribution. Okay? We just need to make sure we take account of those average productivities when we're measuring the capital employed in production. Cool. So then how about the equilibrium of this model? How can we characterize it using some techniques related to those we discussed in the first part of the lecture? Well, what's the steady state equilibrium going to look like in this model? Well, that's going to be characterized by time invariant fundamentals. What are the fundamentals in this model? Well, that's the labor endowment in each country, productivity, and the quality of the capital environment. Eta was that scale parameter determining the average quality of ideas. And then also the matrix of bilateral trade costs and the matrix of capital market frictions. Bless you. Those are going to be the fundamentals in the model. So those are going to be constant. And then the steady state, the state variables are going to be the wealth stock in every country, so A star n. So in steady state, we'll have a constant vector of state variables in each country around the world. And then all the other endogenous variables of the model will be constant, like wages, rental rates, expenditure shares, average return on capital, and portfolio shares. In steady state, the gross return to capital is actually the same across all countries. And that linear var sigma term in the consumption rule actually turns out to be equal to 1 minus beta in steady state. So with log intertemporal utility, it's always equal to 1 minus beta. With CRRA, it's equal to 1 minus beta in steady state. And that means that in steady state, the real return to investment in terms of the consumption good, because just like in macro models, there's a single consumption good here. I either consume it or invest it and create capital, create wealth. And so the price index is the cost of a unit of wealth. And that will be equalized across countries as well in real terms in steady state. So how can we characterize the equilibrium in the model? Well, in the paper we show you can use dynamic exact algebra techniques, sort of pioneered by Lorenzo Caliendo at Yale. So he developed those techniques in a model of dynamic discrete migration. Here we have a model of trading capital holdings between countries. So we don't have any migration, but we have dynamics in capital. And we show that you can generalize those dynamic exact algebra techniques. And if you give me the initial values of the endogenous variables, and the economy is somewhere on a transition path to steady state, doesn't have to be in steady state, it can be anywhere on the transition path to some unobserved steady state with constant fundamentals. As long as I see the initial values of the endogenous variables, in particular the initial expenditure shares for trade and portfolio shares for international capital holdings, and I see 2 periods of wealth, so I actually need 2 initial periods of wealth, then I can solve for the transition path in the absence of any further changes in fundamentals, and I can solve for the transition path for any counterfactual convergent sequence of future fundamentals. Okay, so we can use our dynamic exact algebra techniques and solve for the transition path in the nonlinear model. Okay, but that's just a numerical algorithm. Something else we can do is actually linearize the model and then characterize that transition path in closed form. And so I just want to kind of advertise that to you and why I think these sort of techniques are exciting and could be used more widely in international macro and trade. So we're going to think about, again, as I said, we observe the economy at some initial time. It's somewhere on a convergence path to some unobserved steady state that would arise if there were no further changes in fundamentals. We're going to use a tilde above a variable to denote a log deviation from this initial steady state. And then we're just going to do our standard macro, total differentiation around that initial unobserved steady state. Okay. And what is that going to give us? Well, just like in the trade model, we're going to get a big system of linear equations. In the trade model, it was a pretty small system of linear equations. We just had the n equations for each country for wages. Here now we've got this, when we differentiate all the equilibrium conditions, we've got a larger system of linear equations. But if you play with that system enough and you just substitute one equation into the other, you can actually reduce it down to a second order difference equation in the state variables, second order difference equation in wealth. And so you can use all of the techniques you're familiar with from the dynamic, stochastic, general equilibrium literature in macro. You can solve that system of second order difference equations. You can either use Blanchard-Kahn, you can use Chris-Simms method, you can use the method of undetermined coefficients. We use the method of undetermined coefficients. And so in the linearized model, you can actually get a closed form solution for that transition path of the state variables. What does it look like? Well, it takes the following form. The vector of state variables at time t is some function of the sorry, just back up a little bit. When you solve that system of difference equations, you obviously have to make an assumption about what's happening to fundamentals when you solve that system. So one thing you can assume is no further changes in fundamentals, and then you can solve that system to the unobserved steady state. Other assumption you can make, and it's going to be the one I'm illustrating here, is you can imagine we see our economy somewhere on a convergence path to steady state, and then we're interested what would happen if there's a trade cost shock, or what would happen if there's a productivity shock. And we take a one-time unanticipated shock to fundamentals, and then we solve for the evolution of the entire transition path given that one-time permanent change to fundamentals. And so I'll show you that solution here. In the appendix of the paper, we provide more general solutions. You can solve it again for any assumed convergent sequence of future fundamentals. It's just obviously to solve the difference equation, you need to make an assumption as to what is happening to fundamentals. So in the case of this one-time change in fundamentals, that solution takes a particularly simple form. The evolution of the state variables just depends upon an impact matrix, R, which determines the initial impact of the shocks, so F tilde. So what are these shocks? They're shocks, one-time shocks to fundamentals of the model. So that's productivity, quality of capital, capital market frictions, bilateral trade frictions. These are sort of weighted averages of the bilateral frictions because trade and capital market frictions are bilateral rather than the country characteristics, so you have to weight them in the right way by the initial shares. So those are the shocks we're feeding in. And then R is an impact matrix, which is the initial impact. It characterizes the initial impact of the shock on the state variables. And it just depends upon the observed expenditure shares and portfolio shares and the parameters of the model. So if you give me the expenditure shares and portfolio shares and the data, and you give me the parameters of the model, I've got a closed form solution for R. I can just calculate it. And then after that initial impact, how do the state variables update? Well, they're just going to update according to the simple AR1 process, where the matrix P here, we call the transition matrix, is going to govern the updating of the state variables. And again, that transition matrix just depends upon the observed trade shares and portfolio shares and the parameters of the model. And when you get that solution to the second order difference equation, this transition matrix actually has this eigendecomposable form. And so in fact, I can actually represent it in terms of a diagonal matrix of eigenvalues, capital lambda here, and then the corresponding left and right eigenvectors. Okay, so not only do I get this linear solution, this is obviously in higher dimensional space because I've got n countries, and then I'm shocking these fundamentals. Whereas I can actually reduce this down to n eigenvalues and the corresponding n eigenvectors. So I get a lower dimensional representation of it. And again, I can compute all of these things from the observed expenditure share and portfolio shares and parameters. You just give me those, I can solve for the P and the R matrix, and I can solve for their eigenvalues and eigenvectors. Okay. What does that mean? It means I now can solve the transition path of the economy in closed form. I don't just have a numerical algorithm in the nonlinear model, I can analyze it in closed form. And so that makes it very easy to think about when you change parameters, what does that do to the speed of convergence to steady state? When you take a different parameter value, how do the dynamic properties of the model change? That becomes trivial because you just simply change the parameter and then recompute these matrices. So it makes it very, very tractable to characterize the properties of the model analytically. Okay, so let's illustrate what we find in the last few minutes, make sure that I finish on time. I want to keep us all from dinner and drinks after the lecture. So we implement the model to the bilateral trade data we used earlier, and then also the national accounts data from the Penwell tables. So we match the GDP data in the Penwell tables, the population, labor compensation, capital stock data in the Penwell tables. And then the way we use the capital holdings data is we use it to compute shares and apportion the Penwell tables capital stock across all the investor countries. So we're exactly matching the national accounts data and using the capital holdings to construct the unobserved wealth distribution. And we're going to build on really important work here in the GCAP project that sort of pioneered this sort of frontier approach to measuring global capital holdings, where we're going to restate all the data to deal with tax havens, restate them from residence and nationality. And then we make standard assumptions about all of the parameters of the model, discount rate, trade elasticity, and so on. The one parameter that's probably the least standard is this investment elasticity here, where we take a value from some of Moto's earlier work, where he's trying to estimate that elasticity. What do we get out of this framework? Well, as I mentioned earlier, it explains this property that gravity is not just a good property of the trade data, but it also holds very strongly in the capital data. So even though we don't physically ship stuff between countries as we do for trading goods, if you run a log linear gravity equation for capital holdings, you get an R squared pretty close to the value for a trade equation. And that's even true if you partial out the fixed effects, you see very similar explanatory power. And see similar patterns if you use Poisson pseudo maximum likelihood as well. What do we get out of the model by generalizing it in this way? Well, we actually get this sort of really key insight for the process of economic growth and convergence, which is that when you open up the Ramsey model, you slow down the rate of convergence to steady state. And I'm now going to kind of illustrate that. I'm going to illustrate that by showing the impulse responses of the model with respect to a productivity shock in a country. And you think about the country starting from steady state, and I'm interested in what does this productivity shock do to the steady state capital labor ratio and the endogenous variables of the model. In the in the second panel here, I'm going to show you the impact of this productivity shock in a small country. This is Belgium that we're showing this for in the model, in the quantitative model, and I'm just shocking Belgium's productivity and solving for the transition path to steady state. Second panel here is the closed economy Ramsey model. So what happens in that model when Belgium gets more productive? Well, no surprises. Steady state capital labor ratio goes up. Because I'm in financial autarky, the only way I can accumulate capital is by saving. And so there's no immediate impact to the productivity shock, but I gradually accumulate wealth over time. And because I'm in financial autarky, wealth in the top line is equal to capital in the bottom line. And those solid blue thick dashes give me the transition path, smooth convergence to the new steady state capital labor ratio. And wealth rises equal to the capital stock, very, very standard. So that's the standard closed economy Ramsey model. Everything comes through perspiration. I have to save in order to respond to this productivity shock. What about if I open up that model? So in the second panel here, we've got a version of our model where we eliminate all trade and capital market frictions. So there's a single global portfolio in the world. Capital markets, there are no frictions. Everybody holds the same global portfolio. And I'm now going to shock productivity in Belgium. What does that do to wealth in Belgium? Well, it does nothing because there's a global portfolio and Belgium is small relative to the world economy. So that productivity shock has a trivial effect, negligible effect on the return to that global portfolio. But because I've got a frictionless capital market, when I increase productivity in capital, there's going to be immediate reallocation of capital towards Belgium. So the Belgian capital stock's going to jump immediately as there's this instantaneous flow of capital because this is an open economy model with no frictions in goods or capital markets. And then the final panel just shows you that again, if I let the elasticity in the capital equation, epsilon, go to infinity, and that's actually the open economy Ramsey model where capital is perfectly substitutable and there are no frictions. And again, you just get this instantaneous jump in capital, which is obviously larger when you have a bigger capital elasticity. So what does our model predict, and why does it give these new insights for the growth process? Well, our model generates predictions in between those extremes. The extreme that everything's perspiration versus the extreme that you get all of the capital you need from abroad. So what happens in our model is when there's a shock to productivity and capital, it's going to increase the rental rate. Belgium faces an upward sloping supply function for capital, so it's going to attract a little bit more capital. But we're not going to get this sort of instantaneous flow that equalizes rates of return. The rate of return is going to go up and there's going to be an incoming flow of capital. So there's an initial increase in capital. But we don't get all the way to steady state. We need to do some of the adjustment through perspiration, through accumulation, because there are these capital market frictions. We can't get everything from abroad in a frictionless way that we could in the open economy model without frictions. And so from that point onwards, there's a gradual process of convergence to the new steady state. And what I've done in the second panel is I've overlaid the dynamics from our model, from this far left panel, as the blue, as the purple thin dashed line here. And so what do you see when you compare our model to the open economy Ramsey model? Well, you see we get this immediate reallocation, which dampens down the impact of the productivity shock on differences in rates of return. And then you get convergence to the new steady state. So because you get the initial reallocation that dampens down the variation in rates of return, the convergence to steady state is actually slower. Okay, you cut this line from above and then remain below it as you gradually converge towards steady state. And so opening up this model, allowing for these capital flows, generically gives you slower convergence towards steady state. And there are a couple of other sort of forces in the model that act in that way, which I'm getting kind of short on time here, but I'll just briefly mention them, which is that as you accumulate capital in our model and you produce more output, there's a negative terms of trade effect because you're selling differentiated goods, and because of gravity friction, you're selling them locally. And so that also tends to dampen down rates of return to capital as you accumulate capital and induces slower convergence. Okay. And similarly, because you face this upward sloping supply function for capital, as you accumulate capital, that continues to bid up the cost of getting capital from abroad, and that also acts to slow convergence. And so one of the key insights we get out is that there's slower convergence to steady state in response to this productivity shock. What else do we get out of this model? Well, we get very, very different predictions for deglobalization. Okay, and so I'm just going to illustrate that for trade frictions and then highlight that our model also generates interesting predictions for capital frictions. So now here I'm showing you the impact of an increase in, and I'm going to focus on an increase in US-China trade frictions. And in the left panel, I'm going to do that in a model with capital autarky. So that's essentially the closed economy Ramsey model, just with trade between countries. And then in the third panel, I'm going to do that same increase in bilateral trade frictions between the US and China. And here it's a 50% increase in trade frictions between them. And I'm going to look at that in our model where you have open capital markets. And so let's think about what the effects of this productivity shock are. Well, let's start with the closed economy Ramsey model, Well, if we look at consumption in the top panel, when there's an increase in trade frictions between US and China, unsurprisingly, US and China consumption drops immediately. That's just the static welfare losses from higher trade frictions. There's a static welfare loss because this is a differentiated goods model of trade, standard ACR style static loss from higher trade frictions. Some countries in the short run actually see their consumption go up, like Mexico in this example. Why? Those are those cross-substitution effects we talked about earlier. That now it's cheaper, it's more expensive for Chinese goods to get into the US market, so US consumers substitute towards Mexico. It's exactly that cross-substitution effect. And then what happens over time, well, already in this Ramsey model, we've got something we don't see in standard trade models. We've got this gradual decumulation of wealth in the US and China. Why? Because the increase in trade frictions raises the consumption price index, which is the cost of investment here. So not only do you get static welfare losses, you raise the cost of investment, and so you get this gradual decumulation of wealth in the US and China. And some other countries accumulate wealth over time, like Mexico. Why? Because those cross-substitution effects also increase the return to investment, and so you get capital accumulation. But as you notice here, we actually get quite a different pattern of dynamics for capital and wealth in the US and China in our model once we open up capital markets. Why? What's going on here? Well, on impact, we again get the same static welfare losses, and they're bigger for China than US because the US market is more important for China than the Chinese market is for the US. And over time, we get decumulation in the wealth for the US, but we actually get accumulation in wealth for China. What is happening there? Well, it's the combination of a whole bunch of things. One of the things that's going on is that as China can no longer sell its goods in the US, those goods go back home. That bids down local factor prices and the local consumption price index, which raises the return to investment in China. And that explains why China starts to accumulate a little bit. In contrast, in the US, once those higher frictions go up between US and China, and the US loses access to all those goods from China, its consumption price index goes up. And that raises the cost of investment and leads the US to decumulate capital. Additionally, once we're in this world of open capital markets, now all of a sudden you can get these very strong third market effects where you start to see capital reallocating to other countries. Why? Because when bilateral frictions between the US and China go up, I can now move my capital to other countries and serve those markets from third countries. And so this sort of highlights how opening up capital markets can really change the impact of policy frictions, such as changes in trade costs and changes in capital market frictions. And so I'm kind of out of time here, so I'll just try to stop there. I know it was quite a lot and a little bit quick in the second half of the lecture, but I hope that gave you a flavor of how you can kind of take some tools from trade and try to do some arbitrage to bring together trade and international macro. I think there's so much exciting work to do here, trade learning from international macro, and there's some kind of symbiosis between the two fields. We tried to illustrate that by thinking about a model when we kind of open up the Ramsey model to allow for trading goods and international capital holdings. We try to model trading goods at a point in time, capital holdings at a point in time, and the endogenous accumulation of capital over time. We show our framework can make sense of a number of key features of the data, gravity equations for trading capital flows, home bias, and so on. And they're bringing in goods and trade market frictions. They interact in systematic ways. We get new insights for growth. Convergence to steady state is slower in our full model with open goods and capital markets. And we get new insights for the impact of changes in frictions, such as trade and capital market frictions. And I should stop there to stay on time. Sorry for running over by, I think, a minute or two. Thank you very much.